Thank you for the opportunity to present here. Thank you for joining here in this session. So I want to tell you about data like this. What you see here is in the rows we have patients, and patients in the actual data set will have some 80,000 patients in Northeast China. In the columns we have symptoms, and in this cartoon the observed data is recorded categorical, plus, minus 1 and 0 for the symptoms. We are after finding subsets of patients that have more or less the same subsets of symptoms. That's indicated here by the color-coded boxes. A subset of patients that has more or less the same subset of symptoms, that is simply what we call a disease for the upcoming discussion. So these color boxes are diseases, and we are after discovering these diseases in our massive data set. I could have told you the same story by saying we are searching for subsets of patients indicated by the vertical color-coded bars. On the side here you see these color-coded vertical bars. They indicate subsets of patients. Going after these random subsets of patients, notice that we are not talking about a partition, because we want these subsets to potentially overlap. We want to potentially allow for some of these people not to be in any of the subsets, because the nature of the data is routine health exams. So there might be people who are healthy, who don't have a disease. And at the same time, we want to have horizontal color bars to indicate subsets of symptoms. So we'll need a probability model for random subsets of patients. We'll need a probability model for random subsets of symptoms. And then we want to link the two. Or in other words, I could describe the thing as I want to have a probability model for pairs of subsets of two sets of experimental units. In our case, the patients and the symptoms, which is indicated here in this little cartoon by the colored vertical bars and horizontal bars. You might notice that some of these boxes and bars are solid lines and some are dashed lines. The solid lines, those are known subsets. In our application, those are simply known diseases. As part of this healthcare exam, some diseases are actually diagnosed, so that's part of our data. There's nothing we have to discover about that. And some of them are dashed. That is what we discover newly. So I essentially gave away everything now, yeah? Because all what I'll do in the remaining 30 slides, I'll talk you through the details of that construction and how to do the computing. I also want to talk you through different ways of formalizing exactly the same question. In particular, those of you who were in Simon's talk just before, he talked about graphical models and hypergraphs. You could tell exactly the same story as inference in a tripartite graph. See here on the right side, on top the circles are the patients. I can't do 80,000 patients, but in the cartoon I have just 10 patients, so we have here 10 circles. The rectangles at the bottom are the symptoms, and they are linked. That is the data. Like the data tells me patient 4 records these symptoms. And the entire exercise, the objective, the goal here is to impute a latent third layer of nodes in between the colored nodes that explain the observed data. Like patient 4 might have the red disease, which is linked with the symptoms down here, telling exactly the same story, just in terms of a graph. And Simon just kind of convinced us we could do the same thing in terms of a hypergraph, and I find that a very nice idea. This is joint work with Yang Ni at Texas A&M and Yuan Chi at University of Chicago. And if you like, you can download verbatim copies of my slides. At this URL, you'll find verbatim copies of the slides, just easier to print out if you care. So all what's coming up now is I'll talk you through the data. I'll talk you through the construction of the probability model. and I'll talk a little bit about the computational challenge. Which also means I don't really have that much to say. So if there's some questions that come up as we go along, please feel free to ask as we go along, and keep more general questions to the end. The data that we have here is we have data from routine healthcare exams in Northeast China. This is a company that goes around small towns in Northeast China with a van, and people go through that van to carry out these healthcare exams. And these vans are equipped to record, like I assume there's a nurse coming along with the van, and they're equipped to take to record a number of variables. There's a long list here, and there's more. We take these variables and we reduce these variables to symptoms by coding it either binary or trinary, depending on the type of the symptom. For example, blood pressure, you might code trinary as normal, low, and high. Other items, you might just code binary as present versus absent. These variables include some known diseases, like essentially part of the data is it's recorded whether a patient has diabetes or not. You have to do a little bit of pre-processing, but it's essentially recorded. Those are the known diseases in my title slide. Then with this data, the inference problem, the goal becomes, in addition to the few recorded diseases, we want to do disease mining, we want to do phenotype mining, we want to find hidden diseases that are not explicitly recorded, because that can assist in planning future tours of the same van that can simply be very useful as a clinical decision support. So the aim now is just discovering additional diseases with this kind of data. A little bit of notation is here already. Cap S, I denote the number of symptoms that are recorded. So cap S is the number of columns in the title slide. Little n is the number of rows, the number of patients. And we have two sets of experimental units. One is the patients, the other is the symptoms. And we are trying to find pairs of subsets that we identified in with diseases. So looking at the data, a first shot of trying to discover some structure there is we could look at the correlation of the reported symptoms, and maybe some kind of some structure might jump at us, but that's not quite the case when you, I see the same thing down there. When you look at that correlation plot, there's no obvious structure that jumps at you. So in the next attempt, what we could do is we could try inference on a graphical model. We could formalize conditional independence structure as a graphical model, and then we could attempt to identify disease with some feature of the graph. For example, we could estimate the conditional independence graph, and we could try to match, to identify cliques of that graph as disease. It's a bit arbitrary, it's a bit ad hoc, because it's not obvious what kind of feature you should use. Another great shortcoming is you're totally losing the link back to the patients. Like, part of that inference model is not any kind of learning about which disease might you want to look for which patient. Alternatively, you might try to do some clustering, some partition of the symptoms to discover diseases. It's kind of a similar idea. But again, one of the obvious shortcomings is there's no link to patients. And also, a partition clustering kind of misses the point, because this is an elderly Chinese population who come to these healthcare exams. Many of them have multiple diseases. There's no notion of only having one disease per patient. And the main thing is there's no link to there's that missing link back to the patients if you just do clustering of the symptoms. To link it back to patients, what we could try is we could try clustering on both dimensions, clustering of the symptoms and clustering of the patients. When we do that on the raw data, we kind of see nothing. When we do it after coding it categorically, some picture starts to emerge. It's a bit difficult to interpret, and there's all the limitations that I already mentioned, like we don't really want a partition, we want to allow overlap, etc. But we'll still get back to these themes later. Much closer to what I'm going to bring up, much closer to our model is thinking about some kind of latent factor model. Latent factor model simply means you take the data matrix, which was the first figure on the title slide, take that n by s data matrix, n is the patients and s is the number of symptoms, and we can try to factor that data matrix, we can try some low-rank factorization into n by k and k by s, where cap k becomes now the number of latent diseases that are underlying this. If the data matrix is just a binary matrix, then this becomes low-rank factorization of binary matrices. And this is actually one thing that people do in disease mining. In applied math, they have extremely computationally efficient algorithms to do the low-rank factorization, and it's quite clever. But of course, what you're totally losing is there's no probabilistic interpretation. If you try to have some decisions riding on top of that inference, you need probabilities. You need formal statistical inference. But it's coming already very close to what I'm going to propose. In particular, if that factorization, if that factor analysis includes a notion of sparseness, if you construct a model in such a way that you encourage sparse factor loadings, then you can start to identify factors essentially with subsets, and you get a very similar inference. And that's exactly what's happening in some of these references. In particular, Rokova and George will pop up again. We'll use that for a comparison in some of the upcoming examples. So once you do like latent factor analysis with a statistical inference model, you even already have probabilities and you get the full probabilistic description. But that is still in contrast to something that's missing the probabilistic interpretation, but very computationally efficient to just think of it as a matrix factorization, low-rank matrix factorization. So I want to advertise a different approach to think about it with the comment that everything I'm going to talk you through here, it has an equivalence in some of these other alternative descriptions. I want to explicitly describe it as inference for the vertical subsets on a title slide and a matched set of horizontal subsets on a title slide. I put a probability model on it. Then we link it with the data by assuming a sampling model, and it becomes reasonably straightforward inference. The benefit of doing that will be it has a very easy interpretation. It tries to exactly go after the main inference goal, the main inference target. The huge downside is at the end of the day, when I complete the description of the model, but many of you can probably impute what's coming up on the next two slides. So I'll describe now a model for random subsets for the vertical ones and horizontal bars, and I'll add a sampling model to it. By the time I'm done, I have a well-defined model, but inference for 80,000 patients will be a bear. If you've ever done model-based inference for random partitions for clustering, when you have done MCMC, posterior simulation for random partition models, you probably know beyond something like 1,000 units, that doesn't really work that much anymore. So that will be the big shortcoming, and the last few slides, as you can see on the right sidebar already, the last few slides will talk about simple suggestions to deal with that. So back to the model construction. What's coming up now is just a probability model for random subsets. Probability models for random subsets of a set of experimental units are also known as feature allocation. And one of the more popular constructions of random feature allocation proceeds sequentially. Like what we'll do now is to construct subsets of patients. We'll go down the patients and we'll allocate them to subsets sequentially. And that model will have a name. It's going to be the Indian buffer process. Say the first patient, is in the first subset. The first patient has the first disease. The second patient might not be in the same subset again. The second patient might have the same feature again or not. In this case, the second patient does not have the same feature again. But the second patient has some number of additional diseases, in our case just one more disease, which becomes now the second disease. I'm including here a notion of labeling the features, in our case diseases. I label them by sequence of appearance, by order of appearance. This is just for representation. It's not important in the end. And so on, down to the last patient. So the last patient does not pick up the first disease, does not pick up the second disease, but has like two more new disease, has one more new disease, the disease number 5 here. In the end, I have now represented my family of random subsets. In this case, we have 5 random subsets. Each random subset is characterized by that binary column, which is essentially indicators for my experimental units being elements or not of the random subsets. And let's give a name to that binary matrix. I'll call it cap A. Part of that probability model for that random binary matrix A is the random number of columns. So what I need is a probability model for a binary matrix with a random number of columns. And the popular probability model of this type is known as the Indian buffet process. Many of you know the construction. So what you do is start, like it's a sequential description following the previous slide. The first patient has some number of diseases. The first experimental unit is a member in some number of latent features, a Poisson number of random features. And then when you come down to the I plus first patient, the I plus first patient is a member in some of the already started features with a probability that's essentially proportional to the popularity of that feature in the previous patients. And the I plus first patient adds some new diseases with a decreasing Poisson rate. If you think of it, that makes sense. If you have already seen 10,000 patients, the probability of seeing a new disease in the 10,001st patient should obviously be less than when you have only seen a few patients. This is a complete description of a probability model for a binary matrix with a random number of columns, and it's actually known as the Indian buffet process. So now we have a probability model for the random subsets of patients. That's a probability model for the vertical bars on the title slide. What I need now is I have to add a probability model for matched paired random subsets of the symptoms. That's the horizontal bars on the title slide. And easy enough. Actually, not only easy enough, it's easier, because when I constructed the random subsets of patients, part of the probability model was a random number of subsets, like the cardinality of that family of subsets. Now that I already have fixed the number of latent diseases, I only need to decide which symptoms are linked with which disease. So all what we do now is, for each symptom, there's a fixed, the number of experimental units, the N, and the cap S, those are fixed, because I know the number of patients, I know the number of symptoms that are recorded. For each symptom, I have to decide now whether it's linked to any of the diseases or not. So all the way down to the last symptom, we just flip coins to decide whether these symptoms are linked with the diseases. And that gives me a second binary matrix B, that decides now that is now my probability model on the random subsets of columns, means the horizontal color bars on the title slides. So at this moment, we have given diseases to patients. We have linked the diseases with symptoms. What's missing now is we still have to link, at this moment, it's a prior construction for the latent diseases. I still have to link it with the observed data. Before doing that, I still want to spell out the coin flipping for the binary matrix B. Here it is, we just use Bernoulli's. BJK are the elements of that binary matrix that decide that links the symptoms with the diseases, and we just use coin flips with some common probability rho with a beta hyperprior. You can obviously think of other models. In particular, one model that you might want to think about is the following. Do you notice there's something asymmetric in my construction? I started out with the random subsets of patients. That was an Indian Buffet process. And then I had the random subsets of columns. That was a different thing. It's not obvious that the joint probability model on A and B is now such that it also corresponds. I could alternatively have started with the columns and put an Indian Buffet process on the subsets of the symptoms, and then done the coin flipping for the random subsets of the patients. By this construction, it's not symmetric, but I could have made it symmetric. To make it symmetric, all what I would have had to do is my prior on the random B would have had to be the conditional prior on the Indian Buffet process. When you condition on the number of columns, then it would be perfectly symmetric. So if that's important, it could be done. There's one more minor twist. Sorry, this should be a cap C JK, like the element of the C matrix. Not all symptoms, when symptoms are binary, all what you have to do is you have to decide whether the symptom is linked with the disease or not. When symptoms are trinary, like low blood pressure, high blood pressure, or reference range, when they are trinary, I have to decide plus minus 1 or 0. Just use a favorite probability model for trinary categoricals. We use a Dirichlet distribution. Sorry, we use a multinomial Dirichlet. So at this moment, I have a prior for the random binary or trinary matrix on the title slide. All what I have to do now is I have to link it with the observed. I have a prior probability model for the random subsets for the color bars. Now I have to still link it with the observed data. That's reasonably simple. Can you read that here as on the logit scale, the probability for the IV patient recording symptom J is just simply a regression. It's simply a sum of weights. The WJK gives you something like the propensity of a patient who has disease K to report symptom J. The WJK is the strength of how strongly symptom J is linked with disease K. And all what we do is we add up these W's, and you could think of alternative constructions. We add up the strength of linking diseases with symptoms. We add it up across all diseases that are linked with the symptom of interest, J, and that are also linked with the particular patient of interest, I. Then there's like some marginal rate, which could be due to diseases that are not part of our model because we don't have enough power to discover them, or it could be just some kind of background rate or model misspecification rate. At this moment, you might wonder why we need to separate, like instead of having the binary B's, I could have already made the B's something like a weighted entry. Like I did not need to separate the linking of symptoms with diseases and the strength of the link. I could have simply recorded one continuous variable. Could do that. I prefer to separate it because in my mind it's two separate questions. Like, is a symptom linked with a disease? And if it is linked, how strongly is it linked? For trinary symptoms, one-line summary, you kind of can do the same. Yeah. This is simply a log linear model for that categorical outcome. So if J is a trinary symptom, on the right-hand side, there's essentially a log linear model. What we need now is we need two sets of WJKs, one for observing the symptom at the -1 level and one for observing the symptom at the +1 level. And again, the same comment holds. Instead of having the separate weights, instead of separating the entries of the trinary matrix with ±1 and 0 and the weights, I could have made them continuous entries. And again, I prefer to separate it. So at this moment, we have completed a model description, and in principle, we can carry out posterior inference. Still want to point out exactly the same construction I could have described as a probability model for introducing that latent third layer in a tripartite graph. Or I could have described it as by clustering. I could have described it as vertical and horizontal clustering. Instead, I prefer to describe it as random subsets on the two sets of experimental units. However, like when you talk about bi-clustering, there's some literature that introduces probability models, that introduces model-based inference for bi-clustering. But when it's literally clustering in the sense of partitions and non-overlapping subsets, then that misses, that's inappropriate for our application here, as I argued already before. I prefer the model that I introduced on the previous slide. Since we had like random subsets on two sets of experimental units, random subsets is called feature allocation. Random subsets on two sets of experimental units we call double feature allocation, although there really is not much to it, but it's the construction we had before. There's some literature, like in the ORIE literature, who introduced algorithms for this kind of bi-clustering with overlapping sets. But that's not necessarily based on coherent probability models. This discussion here by Garamani, Wood, and Griffiths, that comes actually very close to our construction. They describe it in terms of graphical models, in terms of graphs. Alternatively, you could describe it as a categorical matrix factorization. Maybe let me just jump down here. If you combine the trinary matrix C and the weights into a single matrix, let's call it D plus for the symptoms at level 1 and D minus for the symptoms at level -1, then you can write the log probability, then you can, as a log linear model, you can write the log probability of recording a symptom for a patient. You can write it as a matrix factorization of the patient having the disease weighted linked to the symptom. So in that sense, it can be described as a matrix factorization. This is just by way of justifying the title of the talk. We have carried out some simulations. Let me go reasonably quickly over those simulations because I still want to make it to a discussion of computational methods. So first, a simulation with a moderate number of patients. So in this case, we are just using 300 patients. The honest reason is because we can't carry out our full MCMC for a much larger number of patients. But as you will see, even with such a moderate number of patients, you already have a realistic chance of discovering latent diseases. So what we did was we actually simulated data, so we happen to know the simulation truth. We carried out the inference under the model on the previous few slides. And let me just show you the picture. Here's the simulation truth. This is the matrix A. The rows are the 300 patients. The columns are the 6 latent diseases in that simulated data. This is an elderly Chinese population. Almost all of them have hypertension. So there's like some diseases that you see a lot and some that are less common. The diseases are linked with the symptoms in the simulation truth. For the binary symptoms, this is the simulation truth. For the trinary symptoms, it's this one for ±1. And here's our estimate. And if you want to complain, oh, this looks too good to be true, I will agree. Yeah? This does look too good to be true. The reason why it turns out so good, there's essentially, on the previous slide, I had the misclassification rate. It's negligible. The reason why it works so well is because we cheated. We simulated from the analysis model. We simulated the data from the assumed analysis model. Of course, it works out well. It still shows one thing. It shows that with that sample size, you do have a realistic chance of discovering something. But for a more realistic simulation, we carried out an alternative simulation where we simulated from a different model, actually a latent factor model, and then with continuous outcome, and then we are thresholding. And now we are getting down to more realistic misclassification rates. So we recover the simulation truth of A with something like a 10 to 20% misclassification rate. That strikes me as much more realistic for 300 patients. Yeah? And similar for linking the latent diseases with the symptoms. By comparison, we also use the method of Rokova and George simply because there's software available. And we cheated a little bit. We gave them an advantage by setting one of their tuning parameters we set it in an optimal way, like we happen to know the simulation truth, so we set it in such a way that we get the best possible performance. And that actually achieves comparable misclassification rates, which just is an argument that the model seems to be doing what we want. And that leaves me some time for a discussion of posterior simulation here. When we actually implemented a posterior simulation for the 300 patients, we could still do a full-blown MCMC. And since you don't know the number of diseases, it's a trans-dimensional MCMC. And if you ever did it, you know it's easy to describe, but it never works. Like, it's a pain to actually implement it. But we actually did this now with the actual Chinese data. Oh, there's a twist to it. We had to comply with Chinese regulations. You're not allowed to publish on Chinese data, I assume when it's collected by public funding, before Chinese scientists published on it. So what we did was we didn't use the actual data, we used a replicate using a generalized adversarial net, where you can argue that to the extent to which your statistical inference is driven by low-dimensional marginal distributions, statistical inference is identical. And we actually had the raw data, we were just not allowed to publish with it. So we could actually see what the inference looks like with the original data, and then we could see what the inference looks like with our hypothetical repeat data, and it looks the same. So here's a secret. The plots that we put in the paper are actually illegally based on the real data, but it's indistinguishable, so we comply with China.
Synthetic data, isn't that right?
Sorry?
Synthetic data.
Synthetic data, you could call it, yeah. So this is then the kind of inference that you get. I want to still show you one thing. By way of a caveat, we are not taking that too serious. Like, we would certainly not suggest that you use our machine to replace the nurse in that van or to replace a clinician. But we think the proper role of this inference can be like a decision support system. For any kids, so we have a little Shiny app which lets you then pull up for any patient. You can impute which diseases that patient is linked with, which are linked with which symptoms, and that might assist the nurse or the clinician in making decisions. It could help you plan. Like, this is a company who do that on behalf of Chinese public health authorities, and that might help them plan how to equip that van and what to look for. But I want to spend my last few minutes of fame here to talk about posterior simulation. So posterior simulation for random subsets can be a pain because it was easy to describe the probability model, but to actually implement it, you run into lots of issues. In particular, I would say for more than 1,000 experimental units, you can't realistically carry out the MCMC anymore. I mean, you can push it with all kinds of tricks. For the special case of random subsets that are non-overlapping and form a partition, there has been quite a few suggestions of how to proceed. There are some papers that introduce essentially all kinds of tricks to streamline the computation, including Payne and Malik. There is a whole little literature on introducing parallelizable algorithms, so you can push it from 1,000 to 10,000 or so by parallelizing it. You can use variational inference, like for model-based random partitions that are based on discrete mixture models. There is all kinds of variational inference. And then there's streaming variational inference, which is variational inference that you can update as more and more data becomes available. There is a literature on predictive recursions going back to 1998. If you're familiar with Dirichlet process mixtures, there's some kind of approximate predictive, one-step predictive rule that you could use to continuously update your inference. It's not exact, but it's a decent approximation. What I really want to advertise though is consensus Monte Carlo, which is a very simple idea. It's essentially divide and conquer. We divide our data sets into many subsets. The literature refers to those subsets as shards. So if we have 80,000 patients divided into 80 subsets of size 1,000, that's unlucky. I'm using cap S for the number of subsets, which is distinct from the cap S for the number of symptoms. So boldface vice S is now the shard one of the subsets that I form in the consensus Monte Carlo. N sub S is the size of shard number S. And then you can implement subset posterior inference. You can carry out posterior inference for each of the subsets. And then in the last step, you take the subset posteriors and you combine it to reconstruct what the joint posterior could have been conditional on the full data. In general, there's all kinds of clever ways to do that. In our specific case for random subsets, you run into a problem. You run into the orange problem. In plain English, the problem is that the nature of our unknown quantities, those are kind of local parameters. The unknown quantities that we are after are subsets of those experimental units. The subset posterior for subset little s are subsets of the patients in the little s subset. The subset posterior for subset S prime are subsets of a totally different set of patients, means it's not common parameters. In contrast, if you had inference on some common global hyperparameters, that is relatively easy to combine. You can do all kinds of tricks, and there's a whole literature on that. So the problem of doing consensus Monte Carlo with local parameters, like in random subsets, is that each subset posterior is actually about a different set of parameters, and you have to somehow intelligently piece them together. In plain English, what you have to do is you get, if this is clustering, you get clusters in each subset posterior, and combining them, we have to consider whether we want to merge some of these local clusters or not. That's what the problem becomes. Here's a very simple idea that we did in some current manuscript. It's super simple. One-line summary. We include common anchors, and we are not the first ones to think about that trick. So what we really do is, instead of forming cap S shards, we are forming cap S plus 1 shards. And then we take each of our shards and we merge it with that last cap S plus first subset, which means that cap S plus first subset becomes a subset of experimental units that are shared by all the shards. So now I have split my data into many subsets that are overlapping, that have an overlap built in. Well, and you can impute what's happening now. Yeah? All what we do is we carry out subset posterior simulation for each of these subsets, including the common anchors. And then when we have random subsets that could be clusters, in our case, it's actually overlapping subsets. Sorry, in our case, it would actually be pairs of overlapping subsets, right? Because we have the double feature allocation. But generically, if we have subsets cap F and cap F prime in two different shards, then we shall merge them. In plain English, simply if they share many anchors. If they share many of these common guys. And we have an explicit rule if the fraction of different anchors relative to the fraction of the total number of anchors, if that is if the fraction of distinct anchors is very small, then they are probably the same. Yeah? Then we should probably merge them. It's a very ad hoc rule. In particular, do you notice that in this ad hoc rule, all what we did was we count the number of anchors that are shared. We are not using anything about like subset-specific parameters, which you could. Like you could merge two subsets if they are similar subset-specific parameters. There were these weights in my probability model. We have, like a similar idea appears in a current paper by Kunkel and Perugia. They use it for a totally different purpose, but that whole notion of using the anchors. I could stop here, or I could show you more results and then a variation.
Well, we have about 10 minutes, so, and if we have 5 more minutes.
Okay.
Any questions? Unless you have people have questions.
So then I can talk you through another simple idea, very simple, like embarrassingly simple. Before we get to that other idea, I want to show you how this, so with this little trick, I can now carry out posterior simulation for the full 80,000 patients. It's not big data like with a cap B, but it's certainly too large a data set to carry out full-blown MCMC. Yeah. And in relatively short time, we can this way carry out posterior simulation, and then we get inference that links the symptoms with some of the known diseases, so these are known, and some latent diseases, and these latent diseases you can then look at which symptoms they are linked with, and you can identify them and give them names. I can't show you the link with the patients because that would be an awfully busy picture. I can show you, this is now showing you the link with the patients, not for all 80,000, just picking 1,000 of them. You actually get inference on these matrices. That's the matrix A and cap C for trinary symptoms. But instead of talking you through details of that inference, I want to talk you through another idea of carrying out consensus Monte Carlo. That idea of divide and conquer is known as consensus Monte Carlo for large data sets. And it's a very simple idea, and simple is a feature here. This picture describes it. The description is in terms of random partitions. So in this paper, we just do it for random partitions for clustering. But in principle, the same trick works for any kind of random subsets, although we didn't do it in that paper, we just did it for random clustering. So start out with the original data. In black are the original data. Think of these as being prohibitively many experimental units, like say 80,000 patients. The idea of consensus Monte Carlo is we split it into the red, the blue, the green, and the black, such that we can carry out the clustering in each of the subsets. So split it in sufficiently many subsets such that we can estimate the model-based clustering for each of the subsets. And as a result of that first step, we get the clusters at, we get a large number of clusters. In the next step, we take that large number of clusters and they become our new experimental units. And we cluster those clusters, call those the regional clusters, like regional for the red region, the blue region, the green region. We take the regional clusters and then we cluster the regional clusters and they become now, what's it between regional and global? So level 1 clusters become now, we are clustering them and they get level 2 clusters. Level 2 clusters are simply created by merging level 1 clusters. Using the same underlying probability model. Everything is done with the same underlying probability model. And keep on doing that. In this particular case, once we take the level 2 clusters and we cluster them, we get, it's actually possible to take those level 2 clusters and cluster them all in one go, and we are done. Yeah? In general, you need as many steps as you need to get down to a situation that you can cluster everything in one go. You don't have to split into subsets anymore. The nature of the approximation is that when we cluster the higher level clusters, let's call the clusters at any level, let's just call them our units. Like the units initially are the original experimental units, the original data. At the first step, the units become then the first step clusters. And we cluster them. Then at the next step, the units become the second step clusters. We cluster them, and now we are done. So the nature of the approximation is when we build the step 2 clusters, then we are merging step 1 clusters. We don't allow to break up step 1 clusters again. So the nature of the approximation is that once we do the clustering, that is frozen. The only thing that we allow then is to merge them. Other than that, we always use the full underlying probability model. In particular, we always go back to the raw data that forms these units at each of the steps. You can only do that if the underlying probability model allows you to marginalize cluster-specific parameters. Otherwise, it becomes a computational and housekeeping mess. In the particular example that we carry out in that paper, that is possible. Before spelling that out, let me just spell out what I just told you in the previous slide. So we start with the original data. Those are originally our units. And then we keep on iterating step 1 through 4. In step 1 through 4, we take the current units, we split them into a number of subsets, such that in each subset we can carry out model-based inference. Then the classes that we get, we collect them all together, and those become our new experimental units, call them Y star at this moment. And then the Y star become the units Y tilde for the next iteration. And we keep on iterating as often as we need until we are in a situation that we can carry out the model-based clustering in one go, and then we are done. Like if cap R is the maximum number of units that you can cluster, if the size of the subsets is like if the number of units that we get is less than R, then we don't have to split it anymore and we are done. This we can only do under the assumption that the underlying probability model allows you to marginalize subset-specific parameters, otherwise it becomes way too computationally complicated. But you can actually do that, especially in the case of probably the most prominent of all, the most popular of all, the Chinese restaurant process, which is derived from Dirichlet process mixtures. And that gets me to the summary. So what I tried to convince you is I tried to talk you through some explicit modeling of these pairs of random subsets. We did it on the basis of full probability model. I would argue that in proceeding like this, our modeling focus remains somehow faithful and close to the original scientific question of find latent diseases. Yeah? Many other formalizations kind of take it to a level where you lose your intuition. Computation is challenging, but we think it can be done by appropriate variations of consensus Monte Carlo. Since everything is model-based, one of the common problems is having missing data. It's relatively easy to address because we have an underlying probability model. And it's easy to use informative priors, in particular, to incorporate partially known diseases. And there's all kinds of extensions that could be done, but I think I better stop here. Thank you.
Very good. Thanks very much, Peter. So one question that occurs to me straight away is the sensitivity to the choice of S, so the number of groups that you partition your large data set into. How do you choose that? I mean, obviously it's parallelizable then across the S, but how do you choose S?
So this is a paid-for question because it's a simple one. I have a maximum number of units that I can carry out model-based clustering by MCMC. Say if that's 1,000.
Okay.
If I have 80,000 patients, then I need 80 subsets.
Yeah. But what's that maximum? How do you choose that maximum?
That's based on your MCMC implementation. Yeah. Like just by trial and error, much more than 1,000 things grind to a halt when you do.
But is the solution sensitive to that choice?
Quick answer, no, because the solution is really just an approximation. Like the nature of the approximation becomes a bit coarser the more subsets you split it into. The nature of the approximation is just that we don't allow to split those subsets. They're frozen, yeah? Like once you form clusters, you don't split them again. So of course, the more you form, the more you freeze.
Very good. Any other questions from the floor?
Thank you, Peter. Very nice. You mentioned several times that it's important to do full probability modeling, and in contrast to the AE methods that you mentioned at the beginning. However, I think when you presented the results, that got a bit forgotten. So you presented misclassification rates and MAP results. So I was wondering what aspects of uncertainty of your method would be important to communicate? For example, uncertainty about the diseases and these things.
Good comment. Quick answer, I plead guilty. I plead guilty, I agree. Longer answer, that there's yet another big white elephant in the living room. So on the basis of that model-based inference on the random subsets, you get a posterior distribution on random subsets. We had, was it yesterday morning or on Tuesday morning, we had a nice talk about question-based graphics. It's not at all obvious how you summarize in terms of a picture, in terms of a representation, how you summarize a probability model over random subsets. It's not at all obvious. A quick answer, we did something reasonable, yeah? So for actual communication, you actually don't want the full probability model. You want a single summary. However, if you have a decision that rides on top of it, like for example, when you plan now the next round of sending that van across the towns in northeast China, now I need uncertainties, yeah? Or when a clinical decision rides on it, then you want to know a probability of that patient having these and these diseases is it worth following up on it, yes or no? Following up on it might mean you called it patient in again, or you sent that patient a letter, come to see us. So quick answer, if some clinical decisions were to ride on top of it, then you need a probability model. Maybe more honest answer, yes, in the end I want a single summary, but I trust my single summary much more if it's motivated by a probability model, even if I were not to fully use that probability model. But fair comment, thank you.
Very good. Other questions?
Can I ask a question? I just heard a talk previously and this morning, and the model, they have like around 6 assumptions. So what's the major assumption of your model?
I'm not sure I understood the question. Was the question, if there's multiple solutions, which one do I report?
Yeah, is there any assumption, I mean, for your model?
Should I understand it as, when you think of the problem as a matrix factorization, there might be many ways of doing the matrix factorization. How do I pick one? Is that the question? Thank you, because that's essentially the answer to Leo's question. Like there's no unique answer. You really only have a probability model on it. You put it much nicer than my answer. There's no such thing as a unique solution. Like there's a lot of uncertainty. You somehow have to characterize it. And what you might want to do is, instead of just reporting one point estimate, as I did in the pictures that I showed you, you might want to report something like, it gets difficult now. You might want to report something like the 5 most likely answers, but as I said, it occurs to me that's a stupid thing to do, because the 5 most likely answers might look very similar. You might want to really do something like report 5 very likely answers that look very different, and that actually starts to become a difficult problem. Like, this is stolen from a talk by Emily Fox in a totally different context. When you ask Mrs. Google for a Jaguar, you don't want to see a screen of cats, right? You want to see some cats, some cars, some football teams. So maybe to show like top solutions, you want to show diverse ones. It's actually a difficult problem. I wouldn't have a good answer, yeah? But it's a good question.
Thank you.
Very good. Thanks very much. I know the coffee break is imminent, so I think Peter can take questions afterwards, and we'll break for coffee now. Thanks again to